Hello and welcome to our September webinar of the OR-MEP training series. My name is Matthew Mills. I'm an energy advisor with the OR-MEP program, and I will be the moderator today's session. We have Nick Young with the Association for Energy Affordability, has a really exciting presentation on all electric new construction. A few housekeeping notes and instructions on how to use GoToWebinar. Today's webinar will be recorded and available on the program website within a few days. All attendees are currently in listen-only mode. If you'd like to ask a question, please ask the question in the question box on the GoToWebinar panel. We will do our best to answer the questions in the order that they're received. At the end of the training, we will open the audio line for questions. In order to participate in that discussion, please enter your audio pin located at the center panel of your screen. And then raise your hand in the meeting panel and we can unmute you. As a reminder, this webinar is part of a series of trainings geared towards supporting current multifamily energy program participants and multifamily professionals. We will cover topics relevant to both existing buildings and new construction projects. Our next webinar, Pushing the Envelope in Existing Multifamily, will be on October 24th at 12 p.m. You can register for that on our program website. And while you're there, please be sure to register for our monthly newsletter to stay updated on future trainings that are being announced on a monthly basis. To introduce our presenter today, we have Nick Young with the Association for Energy Affordability, AEA, who will be delivering this training. As a trainer, Nick enjoys helping demystify technical concepts and giving people the tools and confidence to use different approaches that can improve buildings and reduce environmental impacts. He firmly believes that strategies to address the housing and climate crisis are complementary, not competing. AEA is dedicated to preserving safe, healthy, and affordable housing and reducing climate impacts through energy efficiency and building decarbonization. They are very happy to partner with programs like OR-MEP to share those goals. So for some context of why we're here presenting on all electric new construction, OR-MEP incentivizes efficiency measures that result in electric savings. All electricity consuming measures, be it your HVAC, water heating, lighting and appliances, etc., or your electric load reducing features, such as your wall insulation, your attic insulation, window packages, and such, all contribute to increased incentives. So that means that just all electric projects have more electricity saving features, which contributes to maximizing the most incentives available. And as some of you may be aware, OHCS has made policy updates that align with all electric new construction. As part of the 2018 OHCS Project Development Manual update, all OHCS funded projects must be built solar ready and electric vehicle ready specifications. So on the slide, we have a high-level overview of those updates. And to learn more about it, we have included a link above to the PDM update 2018 R1. And with that, I will hand it over to Nick and he can start his portion of the presentation.
All right, great. Thanks, Matthew. Can I just get an audio confirmation that my audio is coming through?
Yeah, we can hear you fine.
Great. Okay. So for the session today, we're going to touch on a few topics. We'll start with why electrify, like why are we talking about this? Go over the basics of heat pumps, talk about water and space heating systems, appliance options for all electric buildings, and then finally, renewables integration for all electric. So let's start with why electrify. There are a number of primary benefits to all electric buildings. The first is safety. Eliminating gas in our buildings gets rid of the primary source of carbon monoxide. And I just looked this up earlier today. Carbon monoxide poisoning kills over 400 people a year in the US and sends over 50,000 people to the hospital, and that's annually across the United States. If we can eliminate or reduce those risks, that's helpful. It also eliminates the source of gas leaks in our buildings, which can cause explosions. It's also healthier, all electric buildings are. So by getting rid of gas, we're eliminating the indoor and outdoor pollution caused by combustion, a major component of which is NOx. Gas cooking also is particularly bad for indoor air quality and health, and this is being borne out by a number of recent studies showing increased rates of asthma in homes with gas cooking versus electric cooking. All electric buildings are also climate friendly. When we combine all electric systems with low carbon or renewable electricity, we can significantly reduce and nearly eliminate the carbon and climate impacts of our buildings. And finally, cost. It turns out that studies are showing that all electric buildings are actually less expensive to build and operate. So there have been extensive cost effectiveness studies in California for a recent code update cycle that are showing lower cost construction for all electric versus gas buildings or buildings with gas and electricity in nearly every climate zone in California and for nearly every building type. Now, some electric upgrade, it does entail some upgrades to electrical service and slightly more expensive equipment, but you save money on gas main extensions, gas connections, meters, piping, and combustion safety testing. So it's not that every building will always be cheaper if you build all electric versus with gas, but on the whole, in most cases, it seems to be cheaper to both build and operate all electric than with gas. So on the climate front, we really have sort of no other option. To meet our climate change and climate impact reduction goals, there are sort of a few steps. The first is energy efficiency, and we've been doing that for a long time. People are very familiar with it. There are lots of programs around energy efficiency. This program focuses on energy efficiency. So that's great, and we're all very familiar with that. The next thing we need to do is we need to decarbonize the grid, essentially eliminate the climate impact of our electricity. And Oregon and other states across the country are working to do that and to reduce the climate impact of our electricity. And once we have carbon-free electricity, that's great. We need to take advantage of that and electrify our vehicles and buildings. So we shift them from burning fossil fuels to using that clean electricity. And then finally, figure out how to decarbonize the remaining fuels, things like long-haul trucking and industry. Those are additional challenges. But for buildings, we really can get there with the first three steps. And really, it's important to know that electrification is already happening. So there are a growing number of multifamily and particularly affordable multifamily developments that are choosing to pass on gas. So these projects on this slide, I believe, are all from California. That's mostly where I work. But of these, I would say the majority are affordable housing. And this is not something that affordable housing developers are being sort of made to do or there are requirements around doing. They're choosing to do this because they're finding that it makes sense for their portfolio, for their residents, and for their communities. So if we want to build all electric, what does that actually mean? What are the things that we have to electrify? So this graph shows residential natural gas consumption. This is data from a survey in California, so the numbers may be slightly different, but the end uses of gas are not going to be any different in Oregon or anywhere else. So in residential buildings, we use gas for a few primary purposes. First is water heating. And turns out you can do that with a heat pump. Space heating, you can do that with heat pumps as well, and electricity. Pools, spas, and dryers account for another certain amount. And cooking is another amount. So all of the things that we use gas for in our residential buildings, we can do with electricity, and we can do very efficiently with electricity. And one thing that will keep coming up over and over when we talk about all electric buildings and all electric systems are heat pumps. And so let's dive into some basics of what a heat pump is. So if you want to explain, or if you find yourself in a position to be explaining what a heat pump is or how it works in as simplest terms as possible, it's essentially something that moves heat from one place to another. So if you can see my mouse here, your refrigerator, which everyone has a refrigerator, moves heat from inside the refrigerator to outside the refrigerator, or to your kitchen, right? It comes out, that's what these vents are for at the bottom. the heat is pulled out of the refrigerator or out of the freezer and then dumped into the room. That's why it feels warm underneath or behind your refrigerator, because it's moving heat from inside to the room. A water fountain moves heat from the water into the air or the room around it. That's how the water coming out of the water fountain is cold, because it actually has a heat pump inside the water fountain. An air conditioner, the sort of most people's easiest to understand concept. It moves heat from inside to outside, right? If you put your hand next to the outside of an air conditioner, you'll feel heat coming off of it. That's heat that's being moved from inside to outside. And finally, we've got something over here on the right, which we'll talk about a lot in a little bit, which is a heat pump water heater. And so what it does is it moves heat from the air or the space around it into the water. So it actually cools off the space that it's in. If they're outside, it's not going to cool off the planet by putting a heat pump water heater outside. But if you put it in a room, you do feel cool air coming off of this. And it's just moving heat from one place to another. So in simplest terms, a heat pump is something that moves heat from one place to another using refrigerant. This is just like an air conditioner or refrigerator, which everyone should be familiar with. So, but what's so great about heat pumps? Well, there are a few things. First is that they are hyper efficient. Heat pumps can be 3 to 5 times more efficient than equivalent gas products, and around 3 times more efficient than like electric resistance products for heating, and we'll talk about that in a minute. Heat pumps enable zero emissions buildings via carbon-free renewable energy. So if we have solar or wind or other carbon-free electricity that's coming into our building or that we're generating on our building, and we use that to power our appliances and power our building, then we don't have any emissions from our building operations. Heat pumps can also utilize on-site solar PV and act as a thermal battery. So this is a little bit of an advanced concept, but the idea is that you can have a heat pump water heater that takes the solar energy from your solar PV during the day and uses it to heat up water and store that water. And so if you have energy from the sun that you've turned into heat and you're storing it, you could call that a thermal battery. And you can do that with a heat pump. Heat pumps also improve air quality, right? We don't have any local emissions from combusting of fossil fuels, be they propane or natural gas or other fuels. So we have better air quality, and they also improve safety, like I mentioned earlier. We don't have gas lines in our buildings. I personally think that 50 years from now, young people will look back and think we were crazy for piping flammable liquids all over our buildings. But it's what we're used to. But there are a lot of benefits to heat pumps. If you want to really get into the nitty-gritty of how a heat pump works, it works using something called the refrigerant cycle. And I'm not going to go into this in huge detail, but the main point to understand is that you have refrigerant that's being moved around in a cycle, and on one side it's at high pressure, and on the other side it's at low pressure. So over here it's super compressed and it is super hot and it's able to reject a lot of heat over here, and over here it's at lower pressure and it's absorbing heat. So if this were an air conditioner, this would be inside and this would be outside, and it would absorb heat from the inside and cool it off, and then it would reject that heat to the outside and dump that heat outside. And if you have a heat pump water heater and it's trying to heat the water would be on this side and the surrounding air would be on this side. We can go into lots of detail on the refrigerant cycle, and if there are questions, we can come back to it. But that's the basics of it. And there are lots of YouTube videos and other explanations out there if you want to dive in deeper. Okay, so let's talk about electric water heating. Water heating is really one of the things that folks are really the most used to doing with gas. And it's so we really want to make sure folks come away from this understanding what your options are for heating water efficiently with electricity, because a lot of folks are only familiar with very inefficient ways to heat water with electricity. So the best place to start if we want to heat water with electricity are heat pump water heaters. So these are some examples of residential heat pump water heaters, and they really come in two varieties. There is a split type, which you see on the left, where you have a tank right here, and you have the heat pump right here. And all that runs between these two is water. It pulls cold water out of the tank, it heats it up, and then it puts hot water back into the tank. So this works like a little boiler, but it's using electricity and it's using the refrigerant cycle. So that's a split type heat pump water heater. And currently the only manufacturer of these available in the United States is a company called Sandon. And another nice thing about this one is that it uses a very environmentally friendly refrigerant, which is carbon dioxide. It has a very low global warming potential. So it's very environmentally friendly refrigerant, very high efficiency, and that's a split type heat pump water heater. But these are residential size. Over here we have combined heat pump water heaters. And these look and are frankly designed to look very similar to the water heaters we're used to seeing in our homes and apartments. And these have essentially the heat pump on top and the tank on the bottom. So they're all connected together. So if you have a very small space and you want to, and you don't have space for like two items, one of these might work. If you want to put one part inside, one part outside, or sort of maximum efficiency, this might be a slightly better solution. But they all use the same principles of using the refrigerant cycle to heat water. So let's see some examples, or at least one example of one of these. So this is a combined heat pump water heater. You've got the heat pump on top, the tank on the bottom. This one they've decided to duct out. So they have louvers on the door for intake air, and then they're ducting it out. You know, I think personally that this install, they were probably planning on doing gas, and then they decided to switch to a heat pump. So they have this kind of oversized room that they don't really need. Really, this could be essentially outside or in sort of like a shed scenario. It doesn't need to be sort of this robustly protected, but yeah, this just gives you an idea of the form factor. And notice one thing you have here is a condensate drain. So anytime you have a refrigerant system, you're going to get condensation, just like you have condensation on an air conditioner, and so you need a way to drain that condensation out. So we also, for larger buildings, you can have commercial heat pump water heaters. So these, to the untrained eye, will just look like a boiler. They're big rectangular boxes that are connected to a storage tank, and they heat the water. The difference is that they use electricity to do it, and they use electricity extremely efficiently to do it. So these, like any other outdoor unit that you have for a space heating system, for like a heat pump or for an air conditioner, these need access to air, right? And so these are typically installed outside, on a roof, in a garage, or somewhere with access to outside air. They can be installed inside and ducted in certain cases, but you want to make sure and check with the manufacturer on that. So this is an example of an installation of one of them from a company called Colmac, which is based up in Washington. And this is an example of a system on a roof to give you a sense of the size of these systems. So sort of like a boiler. Excuse me. This is another example of a system, and I actually had the pleasure of visiting this system earlier this week. This is on top of a dorm at the University of San Francisco, and this is an all-electric dormitory with, I think, over 150 beds, and this is a heat pump water heating system that's serving the entire building. The heat pumps are up here, and the tanks are actually in the ground floor of the building. So the heat pumps and the tanks are separated by a few floors, which is fine. You can do that. They had to make a few sort of adjustments to the design, but it was okay. So these systems are being installed sort of all over the place. And when we do put them in, it's important to consider a few things for heat pump water heating. First is sizing. It's really important for a heat pump water heating system to understand that the optimal sizing is likely to have more storage than a gas-based system. So it's really critical that a design engineer not use the same sizing parameters they would use for sizing a gas hot water system. And a way to avoid issues with sizing is to be sure to engage with the heat pump manufacturer to obtain sizing recommendations. If you just say, hey, engineer who has only done gas water heating systems, I want this heat pump, We've seen in a number of cases that engineer will say, okay, and they'll take their same numbers they're used to using for gas and apply it to the heat pump, and you'll get a system that's really expensive and not optimally sized for a heat pump. With a heat pump, we want more storage and less heat pump because tanks are cheaper than heat pumps are. With gas-based systems, we've been moving toward less storage, right, all the way to tankless systems with no storage. We actually want to go in the other direction with a heat pump water heating system. So that's sizing. The second main thing to keep in mind is the location of the system. So individual systems, like those individual heat pump water heaters we saw a few slides ago, let me go back. So these systems actually can, particularly these over here, I think not so much this one, but these, it's actually possible to locate them inside a unit with no outside air. So this can really make installation and sort of location of these systems a lot easier. Larger units, commercial units, split type units, those definitely need access to outside air, and potentially you could locate them in a room and have it ducted out or some source of makeup air. But regardless of where you put it, you would definitely need to check with the manufacturer and make sure that they'll have a set of installation locations and air requirements, and just make sure you're meeting those. But it's a good thing to keep in mind that these aren't putting off. The only thing that these things are releasing is cold air. So it's not like a gas system where we have flue gases that are dangerous. We need to get them out of our building. The residential heat pump water heaters, they just make the air a little bit colder. And so if you have a large unit and you put this near a heat source, like near a refrigerator, for example, that's putting off heat, there's actually a number of studies showing that it really doesn't have any impact on the heating and cooling in the unit, and it can make installation a lot easier. And then, like I said, larger and central systems will need access to outside air or a garage, and you can duct them if space is tight. So in addition to heat pumps, there are other ways to heat water with electricity. One of those is a point-of-use electric water heater. Now, these exist, and people are familiar with them, and they're very inexpensive in terms of just the piece of equipment. But there are a few things to keep in mind with these. First is that they can significantly increase your electrical service and panel requirements because these are heating all of the water up instantly. So there's no tank. And so when you call for hot water, it's heating all of it up immediately, and it's just with pure electricity. So that can get pretty expensive, and you need big wires and bigger electrical service often. So really the only reasonable place to use these are for fixtures that are used very infrequently and with very low flow rates. So sometimes we see these used in very efficient buildings for like some bathroom in a common area that's like way on the other side of the building, and it's connected to the faucet for people to wash their hands, so it's not freezing cold water, and that thing gets used rarely. And so yeah, it uses a lot of electricity to heat that water, but it's heating so little water that it doesn't have a big impact. So common area restrooms could be a reasonable use case for these, but not apartments, certainly. So that's heat pump water heating. We don't have an explicit question break right here, but I just want to take a moment, and there's just a lot of stuff, to see if there are any questions about heat pump water heating or other types of electric water heating.
Hey, Nick, yeah, we had a few come in, and to everybody on the line, I encourage you to type your questions in the question box. But one of the ones that we had come in is when deciding between an in-unit heat pump water heater versus a central heat pump water heater, are there any cost considerations or differences that make one more favorable over the other?
Yeah, that's a great question, and it's actually something we've been sort of seeing folks really sharpen their pencils on more recently. So, for a lot of, medium to large size multifamily developers, they're used to doing their central gas water heater with maybe solar thermal, right? And that's just the system that they use for all of their buildings. And now when they're switching to all electric, they're saying, okay, do I use these unit water heaters? Do I just keep doing central, but do it with heat pumps? And we're seeing, different teams come to different conclusions. And so my suggestion would be, if you are going into an all-electric project or you're looking at feasibility, I would actually take the time to get pricing for both. We've had projects that have sort of thought, we're going to do central heat pump water heating because we always did central gas water heating. And then they looked at, well, what would the cost savings be for in-unit water heating, or would it cost to save anything? And it turns out there were a lot of cost savings. One, from eliminating all of the recirculation piping that you have to have for a central system. It was only like a small sort of footprint increase. So if you have like larger family units of larger number of bedrooms, finding the floor area to fit a heat pump water heater in that unit might not be a big deal. We've also seen developers who have come up with solutions to sort of maybe make a closet with like the water heater for 3 or 4 units and sort of put that somewhere and have it like a mini plant. So they have like a few of these on each floor of a building. Like, here's the water heater room for these 4 units, and here's the one for these 4 units. So that's another approach. So I would say basically the things to think about are, what are the trade-offs, and what would it take to do central, and what would it take to do unit water heating, and try to get a good price from your contractor. And hopefully you're engaging with a contractor early on to get pricing, to try to make some of these early decisions, and to really try to find folks who have worked on central heat pump water heating before, to make sure that they're asking the right questions and they're thinking about the right things and including the right things, and really look at which one would make sense for our property. That's a great question, though.
Yeah, and that was a great answer to that question. The next one is, why is there more options for the combined heat pump water heaters for the residential versus the split, like the Sandin?
Yeah, I mean, I'm not really sure. I think it's just sort of, that's where U.S. manufacturers have gone. The Sandin is manufactured in Japan. Sandin is a Japanese company, and they import the product to the United States. So no U.S. manufacturers, to our knowledge, have jumped on using CO2 as the refrigerant, carbon dioxide. All of the, let me go back to the slides all of these use conventional refrigerants, whereas this one uses carbon dioxide. So I don't know, this is just what most of the U.S. manufacturers have done. I think partly it's because it looks more familiar to U.S. consumers, and so they feel like it's less risky. But who knows? If these sell like hotcakes, these folks may jump on the bandwagon as well.
Yeah, thank you. Yeah, and I think that's a good point, to keep an eye on the market as the U.S. adopts new
Totally.
techniques, just like adopting things.
Totally.
Thank you for that.
These things are, there's a lot of development happening very quickly on all electric buildings. There's a lot of policy movement happening. And so we're engaging with manufacturers who have products in other markets, and they're looking at bringing them to the United States. So there's lots of sort of movement happening. So if you don't see something that sort of works for your application now, first, there might actually be something out there that, if you kind of tweak things a little bit, it could work. But yeah, check back in 6 or 9 months and you may see different offerings. All right, shall we move on to space heating?
Yep, there's no more questions here.
Cool. Okay, so let's talk about electric space heating. And to sound like a broken record, the first thing we can do is we can do it with heat pumps. So just like heat pumps are an efficient way to use electricity to heat water, same goes for air and the spaces that we live in. So there are a few different versions of heat pumps for space heating that folks might be familiar with for individual apartments or units. One is a ducted heat pump. So this looks very similar to an air conditioner outdoor unit, and then the fan coil inside. And unlike a furnace, where there would be like a combustion component of this, this is using the refrigerant cycle and refrigerant to either heat the air in the winter or cool the air in the summer. You also can get what's called a mini split heat pump. So it's a split type. So this is also technically a split heat pump, because there's an outdoor unit and an indoor unit. Here there's an outdoor unit, and these are all different indoor units up here. But it's called a mini split because the outdoor unit is small. And the other thing to, and these can be ducted or ductless. So these are ductless units, but you can duct them. And the other thing to keep in mind with a ductless or ducted mini split is that it's going to be more efficient than this one right here, because it's going to have a variable speed inverter. Or sorry, it's inverter driven, and so the compressor can vary its speed, whereas these tend to be just on off. These can be decently efficient, but really you can get the highest efficiencies out of mini splits. And ductless units can be even more efficient because they don't have any duct losses, right? Everybody knows, or you've probably heard, that ducts need to be tight, they need to be insulated because you can lose a lot of energy through your ductwork. Well, ductless heat pumps just eliminate your ductwork. So that's another source of efficiency for these systems. And then a third type of system that can be very low cost and therefore appealing to affordable developers in certain circumstances if they want to do heating and cooling with electricity is a package terminal heat pump. So these are like what we're used to seeing in hotels and motels, and we have some projects that choose to go with these. One thing to keep in mind with these is that a lot of times the heating on a package terminal heat pump, it might actually just be electric resistance. So just because it looks like this doesn't mean it's a heat pump. Some of them are a package terminal air conditioner, or PTAC, with electric resistance heating. And so that's going to be much less efficient on the heating side. So you want to make sure if you need something in this format that's maybe a little bit more budget friendly than these items, to make sure it's a package terminal heat pump and not just a package terminal air conditioner with electric resistance. And so one thing to keep in mind when you go with a heat pump for heating is that you also get cooling. A heat pump system for space heating is both an air conditioner and a heater. So you get both. So if you're used to just supplying heating only for your buildings in more mild coastal climates, and you don't have air conditioning, or you're not used to putting it in, heat waves are not getting any milder. And the climate of 20 years from now is probably going to be a little bit hotter than it is now. And so, if you go with a heat pump system, your tenants and your buildings will have cooling when and if they need it to keep folks safe and comfortable during heat events. So we can also do space heating with larger central heat pumps. So for large high-rise buildings, central systems, rooftop package units, all of those are available in varieties that use the refrigerant cycle and that do heating and cooling with heat pumps up to very, very, very large commercial buildings. You can do it all with heat pumps. For space heating, just like with water heating, you can also do it with electric resistance. So this is just to acknowledge that this is a way to heat with electricity, but there are a few considerations, sort of like with the instantaneous electric water heaters. They are much less efficient than heat pumps. They result in significantly higher energy consumption and emissions. They should have a building, if you're going to use these, you should have very, very good envelope and ventilation to reduce your loads first. If you have like a passive house level building envelope, you may have so little heating that you put in one of these and it barely runs ever. And so it's maybe not actually a big deal that it's not efficient because there's so little heat for it to actually do. But if you wanted cooling, you'd have to have a separate cooling system. So in that case, you may as well just use a heat pump. And a key thing to note is that this program does not incentivize the installation of these systems because they're considered the baseline standard code heating system. So now we have an official question break. Any questions about heat pumps or other types of electric heating and cooling?
Yeah, we have one question, and it is, are there any systems that combine the outdoor condenser for both indoor space heating and water heating?
For space heating and water heating, there are units that kind of. So there are units that sort of do all of it. So this system here is called a heat recovery chiller, and this is from a company called OR-MEP. There are actually some of these installed in California. I would imagine there might be some in Oregon and Washington and elsewhere in the United States as well. But what this system is doing is it's doing heating and cooling and domestic hot water all in one big magical unit. So with complexity comes like a requirement for engineering expertise and rigor. So while you know Jane or Joe HVAC contractor would have no problem installing this, no problem installing that, probably be just fine installing this. You may not even, a design engineer might not even be needed to do a system like this. They're very simple, and the market is used to doing them. Something like this, that's doing heating and cooling and domestic hot water, there's a lot of interaction between different things. And we've seen installs that have been successful, and we've seen that have some that have been less successful if the design and installation team wasn't like super dialed in and really dug in there to make sure they understood exactly what was going on. There's just a little bit more engineering to these systems. Now there are so one thing I'm not showing in this is there are systems that are used extensively in Europe that actually do combine heating and cooling and domestic hot water and ventilation into a single unit. It's sometimes called a compact unit or a magic box. It's like the size of a large refrigerator, and it does essentially all of your mechanical systems in a single magical box. Unfortunately, they are not available in the United States right now, but we're a part of a few different efforts to try to get them to bring them to the United States, but no success yet. So as of right now, the only units that do heating and cooling and domestic hot water are these sort of larger combined units, to my knowledge, and they need a little bit more engineering and installation experience to make them successful.
Yeah, great. That was really interesting. No further questions at this time.
Okay, cool. So let's go on to electric cooking. So this is one that often has a very strong emotional component for people cooking and food do. So if we want to cook with electricity, there are sort of three main ways we can do it. We can do it with induction on the left, with what's called radiant electric cooking in the middle, or resistance. So when most people think of electric cooking, and frankly for a long time when I thought of electric cooking, the only thing I thought of was this, right? And everybody has had the experience with these, that they're not that great. And I mean, they're very inexpensive. And so we have projects that install them because they're affordable, they're cost effective, they're durable, and but maybe not the most premium cooking experience. And then when we move up to slightly nicer electric cooking, we have these two that look very similar, but are actually quite different. So this is a glass top range, but the heating works pretty similar to this one. There's actually an element under the glass that gets super hot, and it transfers that heat to the pot or pan or whatever you're cooking. So it sort of works with the same principle as these resistance coils. It just looks a little bit nicer and maybe a little bit easier to clean. And then over here on the left, we have induction, which is a fundamentally different technology than either of the two on the right, and is really the best way to cook with electricity for a whole host of reasons that we're going to go into right now. So what's so great about induction? Why are you banging on about this, Nick? So there are a few things that we love about induction. One, it has the fastest response time of any heating type, faster even than gas. So people have this notion that electric is slow, right? And I've experienced that with resistance electric. Induction works totally differently. It boils water in half the time of any other heating type. It's extremely precise in its heat control down to very low levels. There's less waste heat in a kitchen, and there's no open flames, and only the pan gets hot. So it's actually safer. So just to sort of step back, well, like, how is all this possible? What's actually happening? What's happening is that an induction cooktop works the same way that like a wireless phone charger works. So those pads that you set a phone on top of and then the phone charges wirelessly, it's the same thing that's happening with an induction cooktop. What's going on is the cooktop is generating a magnetic field that is then exciting the electrons in the pan, and it's heating the pan directly. So the cooktop itself is not getting hot. So you're like, why would you cook with half a pan and melt chocolate? What's going on in this picture? The point of this is to show that the the cooktop itself that the chocolate is resting on is not hot. All that's hot is the pan itself. And I actually experienced this the other day. I got a single burner induction cooktop for myself because I was like, I'm tired of talking about this and not actually using it myself. And so I started cooking with induction recently. And the most amazing thing to me was that, one, the room didn't get hot. I wasn't heating my entire kitchen. I was just heating the food in my pot. And two, I could literally put my hand like on the cooktop right next to the pan, and it was totally cool. So the notion that this is safer, it's like, yeah, there's no flames, but it's also just like you're less likely to touch a thing that's hot and burn yourself because there's just not as many things that are hot. So it's great. So all right, that's all well and good, but what about other things? Like what are the challenges to induction? It can't just be this magical silver bullet. So there are a few things to keep in mind. One is cost. Currently, induction ranges are not the cheapest available. So the one you see on the right-hand side is one that's available at Home Depot. And like for an affordable housing development, that's not cheap. And that's probably much more expensive than, the very low cost electric or gas ranges that folks are used to putting in. So induction right now, it's a little bit more expensive. We expect that as all electric buildings, gain traction across the U.S., that more manufacturers will begin, putting out lower cost induction models. And what I would really love to see is a cooktop with sort of the finish and spec of this, which is to say cheap and affordable. But the only difference is these are induction, and I think you could do that for pretty cheap. The second thing is that you need compatible cookware. So pots and pans for induction do need to be what's called ferromagnetic. They need to have some sort of magnetized bottom. So cast iron and many others with a sandwich bottom all work, and there are a lot of affordable options out there. But not every pan will work. An easy way to test is to use a magnet. If a magnet sticks to the bottom of the pan, it will work. So induction, it's fantastic. There are some things to keep in mind. It's not, it's not the silver bullet yet, but I am optimistic that it will gain traction and come down in cost, so that more folks can start experiencing how great of a cooking experience it is to cook with induction. Okay, moving on to electric laundry, which is really just dryers, because washing machines, they just chug the laundry around. They've never really used gas for washing machines. So in terms of dryers, there are a few different ways that you can do clothes drying with electricity. A very efficient way is a heat pump dryer. There are also more standard electric resistance dryers, or you can get a combo washer and dryer that uses electricity. These are pretty common in like small apartments and, maybe more common in Europe than here in America, but you can get them here, and that can be a sort of very space efficient way to include laundry. And these are for residential washers or residential dryers in a unit. For central or commercial clothes drying, if we have a central laundry room, we could do it with an electric resistance dryer like this good old classic Speed Queen that I see in basically every affordable development I ever go to. And Speed Queen does make an electric heat pump dryer. It is currently not available in the US. There are all these great products that manufacturers sell in Europe and in Asia that they just don't think the US market is ready for. And we are trying to plead the case that we are ready for these and we want them, but we haven't quite broken through on the heat pump dryer yet. But I'm optimistic that will happen soon. Next up is electric transportation. So if we have an all-electric building and we're thinking about the all-electric future, we need to think about electric vehicles. So really, in many ways, the EV revolution is here. It's happening, and new buildings need to be ready for it. There are a lot of state and local requirements for EV charging, and Oregon Executive Order 1720 requires EV-ready construction by 2022 in residential and commercial code. So one thing is to consider sizing your electrical service and infrastructure for the EV future so that you reduce future service upgrade costs down the road. One thing to note is that the program doesn't incentivize the installation of EV charging stations, but it's just it's a component of a building that deals with electricity that you may need to think about when you're designing your building or you're thinking about, the electrical service for your building or things like that. Are there questions on cooking or laundry or EVs?
Currently, there's no questions in the question box, but I do share your enthusiasm for induction cooktops. They're great. No.
Yeah, I was like really prepared for it to not be that good. I'd be like, this is gonna all just be a bunch of hot air, and turns out it's not hot air, it's cool air. It's amazing. It was my kitchen was so comfortable when I was cooking. I was like, this is amazing. Okay, so what about renewables? Renewables on multifamily buildings tend to come in sort of two varieties: solar photovoltaic or solar PV and solar thermal. And so this is a sort of question of, do we do one, do we do the other, do we do both? And traditionally, projects have done solar thermal to try to offset some of the energy usage from the gas water heating system. And that's a great application of solar thermal, right? There's really no other way to reduce your gas usage for gas water heating. And so if we use solar thermal to preheat the water, that reduces the amount of gas we need to use for water heating. So these are great systems that can definitely work and are deployed on tons of buildings all over the place. And then increasingly recently, as the cost of solar PV has come down, we've seen more projects that are used to doing solar thermal also start to do PV as a way to reduce and in some cases entirely eliminate or offset their at least their house meter. And depending on the metering and other laws in the particular jurisdiction where you're working or with your local utility, there may be sort of limits on that. But these are sort of the two primary systems. But what happens, right? So this is solar thermal is what we've used for gas water heating to reduce our water heating usage. What happens when we switch to electric water heating or heat pump water heating? Do we still use solar thermal, or do we go just with solar PV? So there are a few things to keep in mind. And in terms of the difference between solar PV and solar thermal for an all-electric building, really it turns out that solar PV is a much better choice in most cases. So solar PV has no moving parts, whereas thermal does have moving parts, pumps and fluids. Solar PV can offset 100% of all of your loads for small buildings, whereas thermal can only offset about 60 or 70% of your hot water load. You're never going to get a thermal system that completely zeroes out your gas usage for water heating. It's just not possible. PV only simplifies the building. You just have one renewable system, whereas PV plus thermal, you have two systems that you have to deal with. So sort of if you were going to do PV anyway, and you're like, do we do just lots of PV or do we do PV and some thermal? It would just be, you'd have a simpler building with just PV. And PV doesn't impact your heat pump water heating design. You don't have to change your system design to integrate with solar thermal. But with solar PV. But with solar thermal, you actually have to be very careful about how you integrate solar thermal with a heat pump water heating design. So with gas water heating and solar thermal, you hook them up, you preheat the water going into the gas water heating system, and you're done. And engineers and contractors have been doing this for decades, and they know how to do it, and they get it done, and it's great. With heat pumps, you can do that, but what we're seeing is that hot or warm incoming water actually significantly reduces the efficiency of your heat pumps. And because heat pumps are so efficient, it actually makes more sense to go with PV instead of thermal. Both of these systems should be monitored for performance. So it's not like PV, you can just ignore it and it'll work forever. You still need to keep track of it, clean it from time to time, make sure your inverters don't fail. There are things that can break on a PV system, but generally, solar PV only is the best approach for all electric buildings. Okay, how about electric infrastructure? An all-electric building, it's just electricity and it's a bit more electricity. So all-electric buildings, they eliminate gas, the main extensions, the meters, interconnection fees, and in-building gas infrastructure. But with all of our systems powered by electricity, our projects will need larger electrical service. So to make sure that we're not getting caught down the line in a project, it's really important that you consult with your electrical engineer early on and ensure that they know that this project's going to be all electric. I need you to, account for for the water heating, for the space heating, for the EV charging. I've seen projects recently that have dealt with like, oh my gosh, we now have to have stacked parking, and that's the parking stackers have to be EV ready, and so that's like impacting their electrical calculation. And so the earlier on you can start to think about this, the better. You don't want to have major changes to your electrical load or your electrical service late, because that can be very, very costly. So to wrap things up, really the all-electric future is now. It's already happening. All-electric buildings, as we've discussed, are better for our health and for the environment. Buildings, we really have to electrify buildings to reduce our climate impacts. There are a number of cities in California, Washington, and Massachusetts that have passed or are considering bans on gas in new construction. So this may be coming to a city or town near you. As cities and states move away from gas, it turns out that new gas infrastructure could end up being a stranded asset before it's paid off. So think about that. If sort of we foresee that in 10 or 20 years, we're going to end up wanting to convert all of our buildings to all electric, do you want to invest in gas infrastructure that you might end up feeling some buyer's remorse about in about 10 years? Additionally, as buildings move off of gas, fewer and fewer customers are going to end up sharing the burden of the fixed system upkeep costs for the gas system, which is going to increase gas rates. And there's a lot of research sort of showing that this is the case. And so it's really important, especially for affordable housing, that we think about that. And we think not just about what's the historical cost of gas and electricity been, but what will the future costs of gas and electricity be as we move away from gas in our buildings, and making sure that we're protected from those cost impacts. And so in short, we really need to think about how we can move as quickly as possible to electrify new buildings now to avoid those future retrofit costs. So that wraps up my my slides. I really appreciate everybody jumping on today and taking time to talk about this, and I'm happy to answer any additional questions there might be.
Yeah, thank you, Nick. That was fantastic. Currently, we don't have any. Oh, we have one person. Gigi has her hand up. Gigi, I'm going to unmute you. Hey, Gigi, you there?
Can you hear me?
Yeah, we can hear you.
Oh, okay, weird, because I'm on my computer. Okay.
No, you sound great.
I was wondering if we can get a copy of this presentation or download the slides.
Yeah, so we will record the webinar and we will post the slides online in the next few days. Should be pretty quick turnaround. I'm happy to follow up by email as well. Yeah. And while we wait, if there's any other questions, I do want to make a plug for if you're feeling inspired by that solar section. We had a webinar a few months ago, maybe in July, that was all things solar. So if you're curious, go check that out. It is also on the website. So we can hang out for a few minutes here while we wait for questions, but I'll give a sign off in a minute. All right, I think that's enough time. If you do have any questions, please feel free to reach out by email. Thank you, Nick. Is there anything else?
Yeah, I think that'll do it. Thanks very much for everyone to everyone for attending. It's been a pleasure.
Great.